Good morning, ma'am. My name is Saitija from Civil Department, third year. My roll number is 23951A02221. Subject Sustainable Energy System. Subject code AEED36. Topic Discuss challenges in large scale oceans energy development. Ocean energy. Tapping the core of the seas, facing the challenges. The vast ocean covers over 70% of our planet, yet we have barely begun to harness their immense energy potential. As the world races to decarbonize ocean energy and harnessing power from waves and tides, emerges as a promising frontier. However, transforming this blue energy revolution from to reality requires overcoming formidable technicals, economics, and regulatory obstacles. The untapped potential, a blue energy revolution, vast predictable power. Ocean energy offers a renewable power source with predictable pattern, unlike intermittent solar and wind energy. Global market potential estimated at 350 gigawatts by 2050. Ocean energy can significantly contribute to global decarbonization efforts. Coastal energy security provides reliable local electricity to coastal nations and islands, enhancing grid reliances and energy independence. Ocean energy represents one of the last great untapped renewable sources on our planet, with waves and tides, energy offering predictable power generation based on lunar cycle and weather pattern. This technology could provide base load renewable powers. The International Energy Agency projects that ocean energy could supply up to 10% global electricity demand by mid-century, particularly national and coastal communications seeking energy security. Technological tests surveying the harsh marine environment. Engineering devices capable of withstanding the extreme conditions of the marine environment present one of the most significant technical challenges for the ocean energy deployment. Dynamic and corrosive conditions, low velocity, high density energy device variety and innovation. Device must survive powerful waves, strong current and relentless saltwater corrosion. Material must reset biofilling while maintaining structural integrity for 20 plus years in some of Earth's harshest environment. Low velocity, high density energy. Capturing energy efficiency from slow moving water require robust and innovative design. Water high density means even slow currents carry sustainable kinetic energy, but extracting it demands specialized turbine and converter technologies. Devices, varieties, and innovation. A wide range of engineering concepts exist for wave energy, including oscillating water columns, point observer, and attenuator, while tidal energy primarily uses underwater turbine. Continuous innovation drives new approach to and reliability. These three are the technological hardest, surveying the harsh marine environment. Engineering for extremes, designing equipment that survives decades of battering by storms, corrosive salt water, and constant motion, while maintaining power generation efficiency. This is the engineering for extreme. Design equipment that survives decades of battering by storms, corrosive salt water, and constant motion, while maintaining power generation efficiency. Economic realities, the high cost of innovation and deployment, high capital cost, initial investment for R&D, prototyping and manufacturing is sustainable. Each device requires custom engineering and specialized material. Operational and maintenance cost, surveying and repairing submerged equipment in challenging conditions is expensive and complex. Access requires specialized vessels and favorable weather. Cost reduction drives. Key areas include structural design optimization, advanced anchoring and mooring system, and developing efficiency array configurations for multiple devices. The economic challenges lies not just in building devices, but in creating commercial va- viable system. Current ocean's energy capital cost 3 to 5 times higher than the established renewable like offshore wind. However, learning curves and economics of significance cost reduction as deployment increases. These are the economic realities, the high cost of innovations and deployment, high capital cost, operation and maintenance cost reduction drives. The economic challenges lies not just in building devices, but in creating commercial viable system. Current oceans energy capital cost 3 to 5 times higher than the established renewable like offshore winds. However, landing curves and economics of significant cost reduction as the deployment increases. The investment gap from promises to profitability, funding challenges. Ocean energy technologies faces recurring difficulties in securing sustained funding and achieving market visibility compared to more established renewable. Scaling invest focus on tidal stream and waves generation as the most mature and sector strategic private public private partnership can de-risk investment and accelerate commercialization. The levelized cost energy (LCOE) remains the critical metric for ocean energy commercially viability. Current LCOE 0.50 per kilowatt hour, significantly higher than offshore wind at 0.08 to 0.15 kilowatt. However, rapid technology advancement experience effect shows promises for sustainable reduction. The industries need patient capital willing to support demonstration first of a kind installation that builds operation track records. This is the investment gap for promises to profitability. Focuses on tidal stream and waves energy has most mature subsector. Strategic public and private partnership can de-risk investment and acceleration commercialization. Annually, $350 billion annual investment need. Estimated required annual invest to reach 2030 deployment target. 60% cost reduction target. Needed reduction in LCOE to achieve grid parity by 2035. 25 plus active projects. Regularity labyrinth navigating legal and political frameworks, length permitting processes, complex institutional framework, environmental impact assessment, stakeholder collaboration, lengthy permitting process. Obtaining consent for water testing and deployment can take 2 to 5 years, creating uncertainty and delaying projects timelines. Complex institutional framework, multiple agencies with overlapping jurisdiction require coordination across environmental, maritime, and energy departments. Environmental impact assessment. Comprehensive studies required to evaluate effect on marine ecosystem, fishes, and protected species. Stakeholder collaboration, integrating views of regularity, developers, test site managers, and local community for informed policies. A critical evaluation of legal, institutional, and political landscape identities, both barrier and enable for ocean energy, streamlined path, and dedicated marine spatial planning how faster deployment rates. The permitting maze, navigating the complex web for regularity approval required to deploy ocean energy technologies in marine environments. Overcoming the challenges, a path forward. Continued R&D and demonstration, policy supports and investment, international collaboration. Focus on standardization. Strategic approaches combining public funding for demonstration projects, streamlined regularity frameworks, and intern sharing can accelerate deployment timeline by 5 to 10 years. The future is blue, realizing ocean energy potential, clear, predictable power, economic catalyst, climate solutions. Thank you.